Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we will derive another one equation, the force exerted by the jet on a stationary curved plate at one end tangentially when the plate is symmetrical. So this is the condition of the plate and the condition of the jet when it is going to strike to a curved plate. So the plate condition is given like the plate is curved. This one you can see, this is the plate is given. This one from here is started, and this part is the plate part. Okay, this is our curved plate. We can see, yeah, and the curved plate is stationary. See how many conditions are given for the plate. First one is given, the plate is curved, and second one is the plate is like stationary. Stationary means this plate is fixed condition. So here you can see the plate is fixed here with a support of hinge is there, so it is fixed. Okay, and the plate also need to consider like symmetrical. The plate also need to consider this is a symmetrical. These are the plate conditions are there. And the next one, the force exerted by this jet. So this is the jet of water, and that is going to strike the plate at one end. So you can see this is one end of the plate, and this is another one end of the plate. So this end we can consider this is inlet of the plate, and this one we can consider this is outlet of the plate. Okay, and the jet of fluid is striking this plate at one end of the plate tangentially. So you can see this is the jet of fluid actually. This is the jet of fluid which is striking this plate at tangentially. Okay, at tangentially, not perpendicularly. Okay, it is striking this one at tangentially and at one end of the plate. So this is one, as I told you, this is one end, this is another one. So now we can see, yeah, this one, let me tell, this is the normal pipe through which the water is flowing, the fluid is flowing, and this is the nozzle part actually, and from this nozzle the water is coming out with a jet speed. Okay, so the velocity of the jet is v, you can consider, and this is the movement of, or this is the flow of jet of fluid through the plate, and it is coming out from this is the outlet from here. Okay, so this line is, this curved line is given for the movement of this fluid which is coming out from here. Okay, so now, so let's consider the jet of water which strikes a curved fixed plate at the one end tangentially. As you can see, this fluid is striking this one at tangentially here, and we need to consider, as I told you, that plate is symmetrical, fixed, curved, symmetrical. So we need to consider first one, some parameters are there we need to consider. Now the parameters is nothing but v. So v equal to the velocity of the jet. This one we can write the velocity of jet, and similarly here you can see this is the v, we can see the velocity of the jet or velocity of the fluid here. So that makes an angle with the x-axis, with the x-axis. X-axis means this one we can see, this is our x-axis and this is our y-axis. So the force which is exerted by this jet with respect to x-axis how much, with respect to y-axis how much, we need to identify. So now you can see the fluid which is flowing through this plate. Okay, so that makes an angle of theta to the x-axis. So here we can write this is theta equal to angle made with respect to x-axis, angle made by jet with, we can write here, x-axis. Okay, now the next thing, so let's consider that the plate is very smooth. So here let's consider that the plate is very smooth, so that why it need to consider the plate is smooth, so that there is no loss of energy. So we can see there is no loss of energy. So how I'm talking about no loss of energy? If the plate is very smooth, then the fluid which is flowing with what velocity here, the same velocity is supposed to leave from this outlet condition with the same V. So when the plate is considered as a smooth one, so we can consider there is no loss of energy due to the impact of water jet. Okay, so the water jet, after striking the stationary curved plate, we can see at the outlet it will come the same velocity, also V here. So velocity of the jet at inlet and at outlet also both are same. Okay, now we need to find out, actually what we need to find out here, we need to find out the force exerted by the jet in the x direction. That is the thing. Now what is the terminology of symmetrical? The symmetrical in the sense, at inlet condition the angle made by the tangents, okay, that fluid which makes angle at the inlet condition, suppose this is theta as I told you, at the outlet also the same angle should be made by this jet with respect to the outlet condition tangent. So if this is same, then the plate is symmetrical. Then we can consider the angle made by the jet at with x-axis. So at inlet and outlet both should be same. At inlet and outlet same angle should be there. Then we can consider the plate is symmetrical. Another one part will be there, that is unsymmetrical. There it will be different, that we'll discuss. Now here we need to find out, as I told you, we need to find out the force exerted by the jet of water, exerted by the water jet in x direction. This one we need to find out in x direction, and as well as we need to find out for the y direction. These two things we need to calculate here. So in the first condition we know that, so here, okay, we know that fx equal to, here we can write this one, fx equal to, we know that this is the rate of change of momentum, or we can write this is the mass per second. This one also we can write the mass per second into, we can write the change in velocity. So the change in velocity is nothing but v1 minus v2. So though you are considering for the x direction, so I'll write here v1x and v2x. So here we can see the fluid which is coming here at this point, that is velocity v. Okay, so this is nothing but at inlet velocity, that means at v1. But we are considering the force exerted by the jet in the x direction, that means in this direction we need to consider. Okay, but here the velocity is v, so, and which makes an angle of theta. So that means this is the velocity v, and which makes an angle of, with respect to x-axis, of theta. Okay, and along with the y-axis, this is y. Now though we are calculating the force exerted by the jet of water with respect to x-axis, so along with the x-axis we need to consider what is the velocity of the fluid. So here the velocity of the jet is given v, but with respect to x-axis the velocity will be considered, this is v cos theta, So this is nothing but v1x, velocity at inlet condition with respect to x-axis. Okay, so here we can write this is v1x equal to, or we can write the initial velocity in the x direction, because we are writing for the x direction only. So now this one we can write, this is v cos theta. Similarly v2x will be the velocity, final velocity in the x direction. So final velocity where? At the outlet condition. So final velocity which is coming out from this outlet with respect to x-axis. So obviously if you find out the component of this velocity, we need to resolve this velocity in two components like x and y. So our flow direction, we have considered this an x direction. So here also we have taken x direction. But here the velocity which is coming out from here, that is in the reverse direction. You can see this is in the reverse direction. So here also we'll get the v cos theta, but here we'll get minus v cos theta. So v2x is nothing but final velocity in the x direction, that is v cos theta, but that is minus v cos theta. Okay, now very simple. So mass flow rate per second, that we already knows previously this one, how to identify this. This is nothing but mass per time. This is mass per time, mass per second. Okay, so this one we can write mass equal to, we can write rho into volume, and volume per time. So this volume for time we can write, this is meter cube per second. So that is nothing but discharge we can write. So you can write rho into Q. In place of rho into Q place we can write rho AV. Rho Q equal to AV. We know that area into velocity. So the same thing I'll write here. Fx equal to, we can write here rho into A into V. And here into you can write V1x minus V2x. That is nothing but we can write it as V cos theta. Here it is V cos theta. And minus of minus, this is minus of minus V cos theta. So you can write this is plus again V cos theta. Okay, this is bracket close. Now V cos theta, 1 V cos theta, that is nothing but 2 V cos theta. So finally we can write this is 2 rho A V square here cos theta. Because V is there, again V square, and this is 1, this is 1, 2. So 2 V cos square theta, V square cos theta. So this is our equation 1. Okay, similarly, we need to find out the force exerted by the jet of water. The second one, we can find out the force exerted by the jet in y direction. Very simple, same method we can follow here, and we can easily find out what is the force here. Now similarly, again let me change this one. I'll consider the Fy. So Fy also similar method. We can write this is the mass per second. Same thing, what we have written there, same thing we can write, the mass per second into the velocity difference. Okay, the change in velocity, that is nothing but V1y minus V2y. Okay, somewhere it will be given, it will be identified from F equal to ma mass into acceleration, then m into dv by dt. This one also I have told you previously. Acceleration equal to, we know that change in velocity with respect to time. Again, this one we can write v mass by time, and this one we can change in velocity, we can write v1 minus v2. The same thing we are writing here, but I'm writing directly here because these things already I have told many times in our previous lectures. Okay, so this mass flow time also I can write, this is rho a v. Here multiply v1 by v2y, we need to identify. So similarly, how we have taken v1x and v2x, similarly we can find out the v1 by v2y. So v1y is the initial velocity in y direction. Here you can see initial velocity at the y direction. Initial velocity normally we need to consider the inlet condition. So the velocity along with the y direction, though the velocity makes an angle of theta at the inlet condition, so we need to resolve this one as x direction, y direction. So x direction already resolved here. So y direction, this will be like v1y. So this one we'll consider, this is v sine theta. This is v sine theta. So let me write here v sine theta minus v2y. V2y is nothing but here in the upward direction here at the outlet condition, this one. So this is v2y. So v2y is here, again you can get it here, same thing, v sine theta. There is nothing changed. So if you multiply this one, v sine theta minus v sine theta. So finally what we are going to get here, Fy equal to, this is this minus this 0, so whole multiply equal to 0. So that means there will be no equation, no value of this force exerted by the jet of water in the y direction. We are going to get 0 here in the y direction. But if it is in the unsymmetrical condition, we'll discuss that one also. So this no need to give any equation here. I hope you understand how to find out these two things. So this is at the inlet condition, this is at the outlet condition. This is a curved plate, force in this direction, x direction and y direction, and this is the result of velocity in this direction. So I hope you understand this two equation what we have derived for the symmetrical condition. And for the unsymmetrical condition also similar kind of thing is there. Only by showing this diagram I'll show you that what is the difference will be there at the outlet condition when it is considered for the unsymmetrical one. Now see, here also the same thing is there, only thing is unsymmetrical, remaining all the same. The force exerted by the jet on a stationary curved plate at one end tangentially when the plate is unsymmetrical. So in the unsymmetrical condition, all the things will be same here. All the things will be same, except if I draw this diagram, except the angle between this plate and this jet. This one is there. This is the curved plate. This is the x direction. This is, you can say, x direction, and this is the curved plate, suppose. Okay, and the fluid which is coming out here, the fluid, let me give in some different color. Now the fluid which is coming out from here, as you can see, this one is coming out with a velocity v. So velocity v, here it is entering here tangentially, the velocity v which is coming out, same velocity without any loss. Okay, now here the angle made by this will be different here. So here what the velocity was there, it makes an angle of theta with respect to x-axis. Okay, this is x-axis, this is y-axis, we have seen, and the velocity of this v makes an angle of theta here, but here it will be different. We need to consider this is phi. Okay, again this is your, you can write x-axis, this is y-axis, and here we need to find out with respect to unsymmetrical. Now the plate is unsymmetrical condition. Okay, so only the two things are different here. We can write this is like theta equal to, here we can write, previously I have written for inlet and outlet condition. Now this is the angle, this is the angle made by tangent, this is the angle made by tangent at the inlet, with respect to x-axis. Similarly, same thing we need to write, but the notation will be different, that is phi. So this is angle made by the tangent of the fluid at outlet, and same axis will be same with respect to x-axis. So here again we need to find out, here if you find out v1x, so v1x will be, as usual, normal will be like previously what we got, v cos theta, and what about the v2x, this will be different. This will be v2x equal to, will get minus v cos phi, this one. So this will be our v2x minus v cos phi, and this is v2y, this is nothing but v sin phi. This is the only difference. And here similarly, the velocity component at the outlet, this is inlet, velocity component at inlet condition. Similarly, at the outlet condition, velocity component v1y, this is normally v sin theta, this one, this is v cos theta, and this is v sin theta. Okay, this is our what, v1x, and this is our v1y. Similarly, we can write this is v2y, nothing but v sin phi, v sin phi. This is at velocity component at outlet condition. Okay, now we can just put this value in the force exerted by the jet of water in the direction of x and y. We can write Fx equal to, we can write this is rho a v, directly I'll write here v1x minus v2x, bracket close. Again here we can write this is rho a v, put the value of v cos theta, plus here we'll get v cos phi, bracket close. And finally we can write this is vv, if you take common here, then we can get this is rho a v square, bracket close, cos theta plus cos phi, bracket close, bracket start, bracket close. This is our Fx. Okay, this one again we can give an equation, suppose. Similarly, the force in the y direction, the force exerted by the jet in the direction of y. So this one again we can write similarly rho a v, this is v1y minus v2y. Now same thing, we can just put the value rho a v, bracket start, and here we'll get v sin theta minus v sin phi, bracket close. Now finally we can write this is Fy equal to rho a v square, we take common outside, and this one you can write sine theta minus sine phi, bracket close. And finally this is our equation 2. So I hope you understand this equation, like how to derive these two things is simple. Only we need to understand that concept of symmetrical and unsymmetrical, and we need to see the tangential direction, how it is acting tangential on the fluid, and the curve plate and the component of this velocity in both places. As I told you, this is our inlet condition and this is at the outlet. Okay. Similarly, I hope you understand this derivations also. Still, if you are having doubt regarding this, you can give a comment on the comment box. So I'll try to resolve your issues. I hope you understand. Thank you all.